And no one else showing up.
Good evening, everyone. Welcome to Albert Einstein Rockstar. So I want to tell you a little bit about my friend Steve Rosen. He is a specialist in cosmic radiation and nuclear astrophysics. He learned relativity from Professor Vanesh Hoffman, a co-author, colleague, and collaborator of Albert Einstein. During the Cold War, Dr. Rosen worked at Los Alamos and at a prominent think tank addressing issues of national defense and science policy. And later, he was a visiting scientist at l'Institut d'Astrophysique in Paris and Centre d'études nucléaires in Saclay. At the end of Glasnost and Perestroika, he helped 400 Russian émigré scientists from the former Soviet Union find employment in their specialties in the United States. His articles have appeared in science journals Physical Review, Nature, Nuovo Cimento, and his op-ed and popular essays in the New York Times, the Wall Street Journal, and the East Hampton Star. His best-selling book, Future Facts, is listed as one of the 100 important books of the 20th century. Nobel laureate Ronald Hoffman said his book, Career Renewal, co-authored with his amazing wife, Celia Paul, is the ultimate self-help manual for the intelligent job seeker. And after a recent stroke, he wrote, Youth, Middle Age, and You Look Great. Dying to Come Back is a memoir. He is also a wonderful storyteller and an amazing friend. Ladies and gentlemen, Steve Rosen.
Thank you, Judy. And Mike, we know Judy and Mike for quite a while. They actually, they're comedy writers. And that helps a lot when you're dealing with Albert Einstein. I want to thank my wife, Celia Paul, who's sitting up here, for her support. For almost 40 years, she has treated me as if I were her equal. How many people have a smartphone? Almost everybody. Why am I asking this question at a lecture on Albert Einstein? Does anybody have an idea? At the end of this talk, you will have an answer to that question. It turns out that your smartphone will not work without Albert Einstein, and I will explain to you why. There are 897 books in the Library of Congress about Albert Einstein. About 19 of them were written by Albert Einstein. I'm writing another book, and who knows if we need another one, but it's a book for young adults. I learned relativity when I was a teenager, and then I met Vanesh Hoffman and learned relativity 64 years ago. I can still remember everything I learned then, but I have a hard time remembering what I'm saying right now. So, wait, bear with me a little bit. See, these are the people I'm going to be talking about. Albert Einstein, I'm going to explain why I call him a rock star. Enrico Fermi was called the Pope of Physics because he knew everything about physics, Nobel laureate. Leo Szilard, Rodney Dangerfield of physics. He was a bit of a weird guy, I'll tell you what. Edward Teller, you've probably heard of, the father of the H-bomb. Johnny von Neumann, maybe the smartest guy who ever lived. And Eugene Wigner, a gentleman. Wigner, Szilard, and Teller all came from Budapest. And they all had the same physics teacher. And they all worked on the atomic bomb. Just imagine how much money we could have saved if we had brought the physics teacher over. They were all people who did not like Hitler. They didn't trust Hitler. Leo Szilard, in particular, wanted Einstein to sign a letter, which you have copies of in front of you, which you can take home, in which Einstein actually signed here in Cutchogue and changed the course of history. He shortened World War II. He came to regret signing that letter late in life because he was a pacifist, and he did not like the fact that hundreds of thousands of people had to die. Now, I'm going to look at human activity from a very Olympian point of view. By Olympian, I mean how the gods on Mount Olympus would look at our activity. And if you look at the lower left corner, so the vertical axis is things that are actually smart or actually dumb. And the horizontal axis is things that sound dumb or sound smart. For example, sounds dumb, actually dumb, invading Russia in winter. I think you'll agree. We have two cases. I think it was Hitler and Napoleon. Not smart. Plugging a power strip into itself to get free power, actually dumb, sounds dumb. I actually know somebody who declared embezzled funds as income on his tax return. Sounds dumb. I didn't make that one up. So on the right hand, lower right, sounds smart, actually dumb, perpetual motion machines. Sounds like a great idea, but it doesn't work because of the laws of thermodynamics and physics. Upper left corner, controlling forest fires with forest fires. Actually works. It sounds dumb, but it's really smart. And putting mold on infections, the same thing. It sounds dumb, but it's really smart. It works. Quantum mechanics. Quantum mechanics sounds weird, but it actually works. Quantum mechanics is either a blurry picture of a sharp reality, which is what Einstein thought, or a sharp picture of a blurry reality, which is what Niels Bohr thought. But I think that the wheel and sliced bread were actually smart, and they sound smart. And Einstein's reality, Newton's laws, natural selection are all actually smart and sound smart. So here are some more great inventions of all time. The upper left is a thermos jug. And you know the joke about the thermos jug? You put hot stuff in, it stays hot. You put cold stuff in, it stays cold. And what's more, it knows when to do what. Air conditioner, that was a good one. And the wheel. And Mel Brooks said the saran wrap was the greatest invention of all. So why am I telling you all of this? Einstein was asked what was the greatest invention of all time. And he said, compound interest. That's a really smart answer. And maybe that's why he's laughing. He was a witty, extraordinary individual. We'll talk more about that. So, 2016, 3 years ago, I'm reading, trying to explain relativity and gravitational waves to the twins, the 6-year-old twins in our family. And there's a children's book I'm trying to read from. They were not interested in relativity, despite my strongest, most earnest professional efforts to explain relativity. This was right when gravitational waves were discovered. One of the great things, we're going to talk about that a little bit later. So all they wanted to talk about was a certain body part of Albert Einstein. I won't tell you what it is, but if you want to know afterwards, you can come up and ask me. So I decided to write a song that would explain this to them. And I'm going to show you the song, and I'm going to sing it with you, and you're going to sing it with me. And it's based on Twinkle, Twinkle, Little Star, and it goes like this. Albert Einstein, what a guy, had more thoughts than you or I. Special relativity, yeah, MC squared is E. So that's special relativity. Now we're going to do general relativity. Gravitation holds us down, it bends light around the town. It makes GPS's right, squeezes space-time oh so tight. It was at this point that I decided I could write a musical like Hamilton. But I have since made it more modest. It's going to be a review. And some of the songs that I have written for this Einstein musical, I will be singing with you. You're going to be singing with me shortly. And you have to sing in order to cover up my voice. So the question is, what made Einstein so famous? And here it is. I would say a star made Einstein a star. And if you'll see over here in the lower left, this was determined by an astronomical observation, and the bending of light because of the gravitational field of the sun was a prediction of Albert Einstein. This angle and Sir Arthur Eddington, who was a famous British astronomer, did the measurement. The angle of deflection was very, very small, but the astronomical equipment at the time, in 1919, was very, very sensitive. The angle is the size of a quarter as seen from 4 miles away. That's what this 1.75 seconds of arc. Now, this diagram shows you how you are to visualize the curvature of space. We're going to talk more about that. That allows the light to bend around the gravitational field. In other words, the sun distorts the space around it, and that allows the light, or makes the light bend. Now, if you do this in astronomy, and you have an object here, you can actually see behind the object. And it looks very similar to a convex lens. This is called gravitational lensing. It's one of the predictions of Einstein's relativity. And it's used today in astronomy. Gravitational lensing. This is what it looks like. Over here is the Earth. And here's some a galaxy. And you can actually see a galaxy beyond. So it magnifies distant galaxies. It extends the range of optical astronomy because of the bending of light. One of the great triumphs of general relativity, and one of the great legacies of Albert Einstein. And this has been confirmed many times. So how does this work? How does gravity bend light? This is how Einstein explained it. You have a guy in a rocket ship that's accelerating upward, and another guy, let's say his twin, in the same rocket ship that's resting on a planet. Einstein was daydreaming when he was working at the Swiss Patent Office, and this is a story, I think it's true. He looked out the window and a man working on a building fell off the roof. At which point Einstein determined or decided that the man falling off the roof, while he was falling, would not feel any gravitational field during that fall. Einstein called that the happiest thought of my life. So here's how he explains the curvature of light in a gravitational field. He said that this is called the equivalence principle. He said that there is no experiment that you can do in either of these rocket ships that will be able to be different. There is no experiment that you can do in either one of them that will be different from the other one. And if that is the case, then the light entering the rocket ship on the left during the short period that the rocket accelerates upward, the short period that it takes the light to cross the rocket and reach the opposite side, the light will not be at the same height on the right side of the rocket over here as it is here. Now this is exaggerated, of course. Well now if that's the case over here, it's pretty obvious it has to be true, even though I've exaggerated it in the diagram. And if these two are equivalent, that means gravity bends light. Wow. How many people thought of that by themselves? Now, this is called the equivalence principle, and there's so this is a birthday present well this is a copy. Somebody made a birthday present for Einstein to demonstrate the equivalence principle. Now, I'm going to demonstrate it to you. This is a copy I made in my basement from yard sale objects that I collected. It's a long tube. It's got a spring in it. It's got a weight in it. Now I put a rubber ducky here, just to be funny. And everybody see it? The weight of this object is counterbalanced by the force of the spring pulling it in. But the spring cannot pull it in because gravity is pulling it down and it's caught on the left. Suppose I were to erase the gravitational field that's holding this down. And this is how I'm going to erase it. If I erase it, the spring should pull the weight inside because there'll be no gravitational field on this object. Okay? And that's the equivalence principle. Now, it always works at home. So cut me some slack if it doesn't work here. Here goes. 1, 2, 3. Anybody want to try it afterwards? Please see me afterwards. That's the equivalence principle. Another way of putting what I said, the equivalence between acceleration and gravitation, is to talk in terms of mass. Now there are two kinds of mass. There's a mass that's attracted by gravity, and the mass that results from change of direction, change of motion, F equals ma, Newton's laws. In other words, inertial mass resists acceleration. Gravitational mass is the mass that's the result of the attraction of gravity. It's not obvious that those two are equal. But Einstein said, yes, they are. So I wrote a song, which I'm going to sing, and maybe if you know, if this isn't love, from Finian's Rainbow, to explain this. And I actually have music, so bear with me a moment. Okay, here we go. There are two kinds of mass. One resists being shifted. Inertial mass is its name. The other resists being lifted. Gravitational mass is what keeps us all grounded. Both of them are the same, they differ only in their name. Einstein proved, you prove, check this out. Okay, enough of that. Enough of that. You get the idea. So this is what happened after the observation of the bending of light in 1919 with Arthur Eddington. These are the headlines in the New York Times. This was front page news. You might call this front page physics. And all of a sudden, Einstein is a superstar. Unwanted superstar. He didn't want it. He didn't like being famous. I'm going to read to you. In 1921, he comes to the United States. I'm going to read this to you because it's important. Journalists were bewitched, charmed, and awed by, quote, Einstein's straightforward simplicity, kindliness, patience, genuine modesty, and naive humor, which almost made one lose sight of his transcendent mental power. Reporters noted the spell of his wizardry, get these words, the necromancy of strange theories that catch the gaping crowd, and the, quote, beauty and terror of his deeper music of the spheres. And these words, curved space, four-dimensional space-time continuum, and so on, appeared to be mystical and very profound. Here he is, getting the full treatment, the royal treatment, is Fifth Avenue and the key to the city. So why do I call him a rock star? Well, if you Google his name and you Google the name of the Beatles, you get about the same number of hits. QED. I have proven my assertion. My definition of a rock star is a person who inspires intense admiration. And ever since I was a little kid, I have admired Einstein. I wanted to be Einstein. I grew my hair long. It didn't help. Einstein was so famous and popular that he gave all kinds of interviews, and reporters took down every word he said and printed it. So Einstein said he had a very weird Midas touch. Midas was a king who everything he touched was gold. Einstein said everything I spoke became print. Oppenheimer, who was the head of the Manhattan Project, knew Einstein at the Institute for Advanced Study, and he described Einstein as friendly, lonely, strange, and with a luminous mind. Studs Terkel, the journalist from Chicago, said that you can't go wrong quoting Albert Einstein. Anything he said was interesting. Now, the other paragraph is from a reporter describing the effect of relativity on the intellectual atmosphere of the time. I'm going to read it to you because it's important. The effect produced by dropping a new thought into an ocean of old ones is like dropping a crystal into a solution. Sometimes the crystal dissolves into the liquid and disappears. Sometimes it sets the whole mass crystallizing in its own image. Likewise, the effect of a new idea depends on its coming at the right psychological moment. I think that's a great description of what relativity did. It exploded physics. The second paragraph is by Banish Hoffman, the man I learned relativity from 64 years ago. And this is from his biography, which I recommend among many others, and there are a lot of books up over here. This is what he says. Fate had played an unexpected trick. The faintly deflected starlight had dazzled the public, and suddenly Einstein was famous. This essentially simple man, a cloistered seeker after cosmic beauty, was now a world symbol, a focus of widespread adoration and of deeply rooted hatred. Admiration by the general public and scientists, hatred, Hitler. Hitler hated him because he was Jewish, because he was a genius, because he got the Nobel Prize, and he was famous. Hitler, in fact, referred to Einstein's physics as Jewish physics, and he meant it as an insult. He said that German physics, he called it Aryan physics, was superior to Jewish physics, because Aryan physics, Hitler said, was experimental, whereas Einstein's physics was inferior because it was theoretical. Hitler had a price on Einstein's head. He wanted him assassinated. And fortunately, Einstein left in 1933 and stayed at the Institute for Advanced Study until 1955 when he died. Here he is enjoying fame for a moment. That's Charlie Chaplin on the right side. This is 1931 in Hollywood, and it's the premiere of a movie called City Lights. And the crowd is cheering. And Einstein says to Charlie Chaplin, "What's all this cheering about?" And Chaplin says, "They're cheering me because they understand me. And they're cheering you because they do not understand you." And then Einstein says, "So what does all this cheering mean?" And Chaplin says to him, "Absolutely nothing." So much for fame. So Einstein really got annoyed with fame. I mean, he actually, there's a lot of stories about him. He was once traveling after he got the Nobel Prize in 1921. Not for relativity, by the way, we'll talk about that. He was recognized everywhere, photographs. So he stopped by a reporter, and the reporter says, "Dr. Einstein, I'd like to interview you for my newspaper." And Einstein says, "I'm not Dr. Einstein." And the reporter says, "Yes, you are. I've seen your picture in the newspapers." And Einstein said, "Who should know better, you or me?" Einstein actually wrote a piece of poetry, doggerel, in German, which I have translated here, and which I have set to music, which I'm going to play. I'm not going to sing this, but you don't have to worry. But it's called Celebrity Fatigue, Einstein's Lament.
Wherever I go and wherever I stay, there's always a picture of me on display, on top of a desk or out in a hall, tied around my neck or hung on a wall. Sometimes surrounded by all this good cheer, I'm puzzled by some of the things that I hear, and wonder my mind for a moment not easy if I and not they could really be crazy.
Now, these are Einstein socks that my relatives and friends have given me, and I'm actually wearing some. I can show you afterwards. But please note that there are 3 distinct socks, different kinds of socks, by 3 different sock manufacturers. Now, I have looked to the history of science and the history of socks, and I have found no other scientist has their face on the manufacture of 3 different socks. So I could have called this talk, instead of Albert Einstein Rockstar, I could have called it Albert Einstein Sockstar. So now I got another song that explained gravitational talking. This, again, I'm not singing this one. Okay, this is very short.
Fame and genius, what liabilities. astronomer Sir Arthur Eddington mounted an expedition that confirmed a prediction Einstein made in 1950, that starlight should be bent by the gravitational field of the sun. It was just gravity's tug, the field of the sun keeping it snug, the light of a star being bent in a hug, just gravity's tug. This result has been confirmed many times. The angle of bending you see in the lower left corner of the slide is the angle made by a quarter seen from a distance of 4 miles. It was so small, like an inch, and 4 miles away, not an inch, bending a beam of starlight above. It's just gravity's tug. And we continue.
So Einstein did not invent the term fake news, but he was certainly aware of it. And I'm going to read to you what he said. These are Einstein's exact words, after he's very famous now. And not enjoying fame. By the way, Einstein insisted that he was not a genius. Everybody else thought he was. I think he is. He said, I'm not a genius, I just stay with the problem longer. Now, I think that's a great message for young people today, because a lot of them give up pretty easily. Here's what he said. Anyone who is sufficiently popular or notorious, as I am, can become victimized by interviewers. One day, a gentleman of the press comes to you and asks you to give him a few details concerning your best friend, Mr. X. Amazed and maybe a bit annoyed by the intrusion on your privacy, you say, my dear friend, Mr. X is a cheerful, straightforward man, much liked by all his friends. He can find a bright side to any situation. His enterprise and industry know no bounds. His job, excuse me, takes up his entire energies. He's devoted to his family and lays everything he possesses at his wife's feet. And here's what the reporter writes for his newspaper. Mr. X takes nothing seriously. He has a knack of making people like him. Excuse me. Chiefly because he flatters everyone. He is such a slave to his profession that he has no time and doubtless no inclination for intellectual pursuits. He is weakly indulgent to his wife. In fact, he's entirely under her thumb and mere putty in her hands. This man is named Banish Hoffman, and he's one of the few people in the history of science that has his name on a paper with Albert Einstein. Excuse me a bit.
There's water.
I'm going to drink some water. So here's what he told me about working with Albert Einstein. This was at the Institute for Advanced Study in Princeton. And he said, so Einstein and I would sit side by side at his desk. And we would be working on the field equations of general relativity, which I will show you in a few minutes. Very, very complicated equations. Excuse me. And even Einstein would get stuck. And Banish said whenever Einstein got stuck, he said Einstein would get up from the desk, he would pace the floor. And he said Einstein had very long hair, just like me. And he would twist his hair, and he would say with a German accent, "Bill, a little thing." And after a few minutes of pacing the floor and twisting his hair, Einstein said, "Aha! Let's make an approximation." So he would sit down, and sure enough, it would work. Bainich said that after Einstein died in 1955, whenever he was working on the same equations of general relativity, and he would get stuck, he would get up and he would pace the floor and twist his hair. You can see that he doesn't have enough hair to do this right. And he said, it never worked. So I wrote a song about this, of course. I can only remember what the melody. Oh yeah, on the sunny side of the street. If I had long hair, could I think like Albert Einstein? Causality misplaced, all that hair would be a waste. It was concentrated thought and staying focused on it. We could do the same, a buzzing bee in our bonnet. Sorry about that. I used to think Einstein's hair gave him a certain flair, but I know it wasn't hair that made him so rare. It was concentrated thought and staying with the problem. That's something I should do, and you should too. You think it's easy to write this stuff? So now we come to the year 1905. I'm jumping around. 1905 was called the miracle year in Einstein's life because he wrote 4 papers. Each one of them would have been worth a Nobel Prize. He only got one, but it was not for relativity, it was for the photoelectric effect. The photoelectric effect is what makes your digital camera work. And the physics is, Einstein was able to explain why when light of a certain frequency or energy struck a metal, it knocked electrons out of the metal. And he had to assume that the light came in little packets or bundles called quanta. So Einstein was one of the first people to begin to develop quantum theory, 1905. And that's what he got the Nobel for. They didn't understand relativity, and it was controversial, so they did, and that was in 1921. Brownian motion. Have you ever seen dust motes floating in the air with the sun coming behind them and they bounce around? That's called Brownian motion. And Robert Brown discovered this with pollen in liquid suspension. Einstein was able to explain Brownian motion by assuming that molecules exist and that they move around and bounce around and knock the pollen just like the air molecules knock the dust motes around in the air. Special relativity we're going to talk about in a minute, and matter-energy equivalence is E equals mc squared. We'll get there. So now I'm going to talk about postulates. In high school geometry, we learned that if you make certain assumptions, simple assumptions about lines and points, you can create a whole universe of theorems, truisms, that are based or consistent with those postulates, such as you can draw a straight line from any point to any point, and so on and so forth. Einstein decided to do the same thing with relativity. The first postulate of Einstein is that the laws of nature are the same for all space-time coordinates. And he called this the principle of invariant. Let me explain this. Suppose there's an accident at 42nd Street and Times Square at noon on Tuesday. I just described that by using one system of coordinates, street, avenue, time. Suppose I said that this accident occurred at 70 degrees west longitude and 47 degrees north latitude at Greenwich Mean Time, 1200. the same event is described by a different coordinate system, the physics should be exactly the same. It might be more difficult to write the equations. It sounds obvious, turns out to be very profound. Suppose a bus is traveling past the accident. The bus has certain coordinates, it's moving. But the accident has the same physics, whether it's seen from the bus or whether it's latitude and longitude and Greenwich Mean Time. That's the principle of, there's no preferred reference system. Basically, it's assuming that physics is the same everywhere. Second, the speed of light is constant, independent of the source or the observer. Now, this sounds trivial, but it's actually spectacularly dramatic, and it changes everything. It, and I'll show you how in a moment, it implies that time is different in a system that's moving with respect to another system. It implies that lengths contract in moving systems, that mass increases, and that E equals mc squared. All of that comes out of this simple, it sounds simple, postulate. And the third, we talked about the principle of equivalence. Gravity and acceleration are identical. Okay, everything's been easy. Now comes the horse. Okay. The left diagram, you would imagine a woman in a train. You have to use your imagination. And a beam of light hits a mirror on the floor of this train, hits the ceiling, a mirror there, and bounces back. The amount of time it takes that light beam to do that is equal to the distance, the height of the train, divided by the speed of light. Okay? That is according to the woman in this train. But now there's a guy standing on a platform, and he watches this train go by. What does he see? I mean, this is exaggerated. He sees that instead of the beam going vertical up and down, it goes up to the right and down to the right. Look at the length of this path. This is D, it's greater than L, and the time it takes for that to happen is the distance it travels, the greater distance than L divided by the speed of light. But the speed of light is the same to the guy standing on the platform because of that postulate. Actually, it's because of an experiment called the Michelson-Morley experiment. We'll talk about it in a minute. So if this distance is greater and the speed of light is the same, this time period as seen by the guy on the platform looking at the train passing by is slower. It's a longer time interval. Correct? Right? It's hard to believe, but it's true. Now, this has been proven many, many times. And one of the ways it's proven is if you look at radioactive decay of particles, if the particle is stationary, it'll have a certain half-life. If the particle is moving near the speed of light, the half-life will be longer. Actually proven. Bizarre. So that's one of the spectacular results of the speed of light being constant. Not only does the speed of light change the view of time in a moving system, but in a gravitational field, the speed changes, the time changes as well. So A to B is a beam of light moving not in a gravitational field. but we saw that the gravitational field makes light bend. So CD is the same beam of light that's bending in a gravitational field down below. That path is longer, so what does that mean? That the light, the time is longer, is longer in a gravitational field and less in a weaker gravitational. Now, why am I talking about this? Remember the smartphones? Remember the global positioning satellites? So we have two effects of relativity. One, because of the speed of the satellite above us, it changes the time that the clocks, very, very accurate clocks in those satellites radio down to us on Earth. And second, because the gravitational field is different. We're going to show exactly how this affects. So that's one answer to the question I asked at the beginning. And another legacy of Albert Einstein. Now, a little harder. This is a diagram of the relativity of simultaneity. And the upper diagram is a car, a railroad car, where light is sent from the center to both ends. And you can see that in a stationary system, as the one above, that the light reaches both sides simultaneously, as we know it. But if the thing is moving, that doesn't happen. So in a stationary system, what's simultaneous is not simultaneous to an observer outside the system looking in. Now, this is an example, or a diagram of the Michelson-Morley experiment in 1887, which proved that the speed of light is the same independent of the movement of the source or the movement of the receiver, the observer. And the way it worked is a beam of light is sent to a half-silver mirror. Part of the light goes through the half-silver mirror, part of it bounces back, it comes back here, recombines, and if the light is in the same phase, it reinforces, and if it's not, it cancels. And you can use this to measure the speed in this direction and in this direction. As you can see, if this Michelson-Morley experiment is moving to the right, like this, then everything changes. And it turns out that the only way the Michelson-Morley experiment can be interpreted is if this dimension, this length in the direction of motion contracts. So now we have time expands, length contracts. You'll have to take my word for it that mass also expands. And here's the first nuclear-powered aircraft carrier with E equals mc squared. I'm not going to show you how that happens because it would take too long, but it does imply a lot of things about the universe.
Those sailors on the deck spelling out?
You know, a number of people ask me that, and I can't see good enough to tell. They look like sailors, though. It's a nice idea, a good sort of Hollywood idea. So now we're going to change gears a little bit and talk about cosmology and how Einstein's views on gravity changed our views of cosmology. Go back to Ptolemy in ancient Greek, and he believed that the stars were mounted on glass spheres that rotated around the Earth, that we were the center of the universe. Of course, he didn't have the Hubble telescope. And this is a beautiful diagram, a medieval diagram, showing these shells, and there were the harmony of the spheres and so on and so forth. So now let's jump ahead to Newton, and it is not a myth that Newton was daydreaming when he saw the apple fall. Whoops. What happened? Okay, it is not a myth. himself said it himself, that he was daydreaming and he saw an apple fall, and he deduced the universal law of gravitation, that the force between two masses is proportional to the size of the mass and inversely proportional to the distance. Now, it is not a coincidence, to my way of thinking, that Einstein was daydreaming when he saw that guy fall off the roof. So, do a lot of daydreaming. And in fact, nuclear magnetic resonance of people's mind when they're daydreaming shows that you are more likely to come up with some creative idea when you're daydreaming than when you're focused on something. And somebody called that the dark energy of the brain. We'll talk about dark energy in a minute. So now we go ahead to the 1800s, and a guy named Olbert asks a really dumb question. Why is the night sky dark? It should be bright, because if the universe is infinite, and there are an infinite number of stars, everywhere you look, every sight line from your eye to a star should end up on a star. How many people have been in a forest, a dense forest, and you look in every direction, whether the trees are close to you or far away? There are trees everywhere. Well, the night sky is not bright, as we all know. What's wrong with this picture? The universe is not infinite, and there are not an infinite number of stars. There's a lot of them. So he was wrong about it. But it was a very interesting question to pose based on the equipment that they had at the time. So here's the picture today based on Einstein's work and a lot of others. It's called the Big Bang. And on the left side is the creation of matter out of nothing. Now, how can that happen? I got a rubber band here, and what happens when I stretch it? I add energy to it, right? I'm stretching it. What is energy? Energy is a form of mass. Mass is frozen energy. Mass and energy are equivalent. So I'm adding energy, I'm adding mass. Well, suppose space, empty space, and there is no such thing, empty space was stretched, that could create mass because you're putting energy into it. And that's where the origin of the Big Bang, at least our thinking now. 14 billion years later, we have what brings us to the present. So what happened before the Big Bang? Stephen Hawking answer. He says, asking the question what happened before the Big Bang is like asking what is south of the South Pole. Think about it. So here's how stars evolve into supernova, and upper diagram is low mass stars, and high mass stars end up as neutron stars and black holes. And I'm going to try to explain to you how you can measure the curvature of space. We could pass. This is an object I made. It's flat, and I made a triangle on a rubber glove. 3 squared is 9, 4 squared is 16, 5 squared is 25. Pythagorean theorem, right? For a plane right triangle. That's this. But suppose I take that same square, or triangle, and I put it on the surface of a volleyball. This is a two-dimensional plane. This is that plane curved into a third dimension that's perpendicular to the plane. Okay, now this is a metaphor, a simile, or an analogy to four-dimensional space-time curvature. Do not try this at home. No one can visualize that four-dimensional space-time curvature. But you can discuss it mathematically. And so, one way to measure the space-time, the curvature of space, is to see how far this departs from this. And I call this Pythagorean, and this is departure from Pythagoreanicity, Pythagoreanness. Well, mathematically you can do this with four dimensions and measure how far space-time, curved space-time departs from flatness. Have you suspended your disbelief? Okay, now, do not be frightened. These are equations. The first one is Newton's law of gravitation, which we may have learned in high school, and I just mentioned that the force between two massive objects, capital M and little m, depends on, is proportional to each one, and inversely proportional to the square of the distance. This tells you what gravitation does. It tells you the effect of gravitation. The second equation is Einstein's general relativity. And let me translate this into words. On the right-hand side is mass and energy. On the left-hand side is curvature of space. So this equation in words says mass energy tells space-time how to curve, and space-time tells mass how to move. That's a one-sentence summary of general relativity. Now, this tells you what gravity is. It's the curvature of space-time. This tells you what gravity does. Anton Chekhov wrote a letter to his brother, giving him some advice about how to write. And this is a quote. He said, "Don't tell me the moon is shining. Show me the glints of silver on the shards of broken glass." The difference between tell and show. This is tell. Newton is telling you what it does. Einstein is showing you what it is. We're almost finished. This is not a photograph of two black holes. This is a computer simulation of two black holes at a distance of about 1 billion light years away. Each one of them about 30 solar masses, and they're a binary system. They're orbiting each other. And here we go. Okay, so I'm going to start this computer simulation. This is a solution of those complex equations of general relativity that you just saw, with huge amount of computer power, showing that these two orbiting black holes are going to collide and spiral inwards. And when they finish, the total mass of the single black hole will not be 60 solar masses, it'll be 55. And what happens to the 5 solar masses that's not there? It was radiated away in the form of gravitational waves. And this was how the discovery of gravitational waves several years ago was explained. So now, ready? Here goes. Now, what you're seeing, the reason the star field behind it is distorted is because of the curvature, the very, very strong gravitational field. It looks like two donuts or two bagels. They are about to merge and then send off gravitational waves of 5 solar masses. The sun weighs 10 to the 33 grams. Okay, there it is. This is the result of 1,000 physicists around the world. The experiment to detect these gravitational waves, I'm going to show you how that looked in a moment, cost about $1 billion of your money, and I'm going to show you where your money went. So this is an interferometer similar to the one, the Michelson-Morley interferometer in 1887, but this took about 40 years, and the guys who did it got the Nobel Prize, deservedly so. Let me explain how this works. There are 2 arms, it's called LIGO, Laser Interferometer Gravitational Observatory. You're going to see a laser beam coming out here. This arm is about 2 miles long. This arm is about 2 miles long. The beam is going to go to the split mirror. It's in a vacuum. And it's going to, one beam is going to go there, hit here and bounce back. The other beam is going to go here, bounce here, and come back. And on the screen, if the 2 lengths of these arms are the same, the light beams will combine in phase and reinforce each other, and there should be a bright spot over here. If the length of one of these arms changes by as little as 1,000th the diameter of a proton in 2 minutes, the light beams will cancel each other out, and you'll see a dark spot here. That's where your taxpayer money will be. Watch this. Okay? Now, it was well known that Einstein was a ladies' man, and there are documented affairs that he had, including one that may have been with the Queen Mother of Belgium. They had a very intimate exchange of correspondence. We don't know for sure. But women seem to like him. This is a cartoon from the New Yorker, and the woman is frowning and she's smoking a cigarette. One can only imagine what happened right before this scene. The caption, Einstein speaking, says, "To you, it was fast." So now we're winding up. What good is physics? The GPS, the Global Positioning Satellite, cost you $10 billion. The purpose was for military navigation. There are 24 satellites up there. The clock, there's an atomic clock in each of them, accurate to 50 billionths of a second. The altitude is 20 kilometers. They're going around the Earth twice daily at the speed of 14,000 kilometers an hour. The application, airplane navigation, wilderness recreation, bridge construction, sailing, interstate trucking. In Hollywood, James Bond devised the evil genius who's putting deliberate errors into the global positioning satellite. So special relativity, because the satellite is moving fast and because the time in this moving system goes slower, the clock ticks 7 millionths of a second per day slower because of the speed, special relativity. Because of its altitude, its distance from the Earth, general relativity says, since the gravity is 4 times weaker, the clocks are faster by 45 millionths of a second. You can do the arithmetic. That's why you're carrying Einstein around with you. So I want to just wind up by pointing out that Einstein, you have a copy of the letter that Einstein wrote. He regretted signing that letter because of the lives lost. He was a pacifist, yet he believed that the Germans were ahead of us, and he hated Hitler, and Hitler hated him. So I would like to say two things. One is that he charmed and invigorated civilization. He exploded physics. He had a brilliant, whimsical mind, a first-rate temperament. He insisted he was not a genius. His secret of happiness: read no newspapers. And here's the last word. This is Einstein talking. Here's how a wired telegraph works. It's like a lone cat. You pull the tail in New York and it meows in Los Angeles. Radio wireless is exactly the same, except there's no cat. One last thing. I'm going to sing you one song. There'll never be another thing like him, and I can't seem to find. Anyway, this is a cartoon by Herblock, 1955. Albert Einstein lived here. And so here's the song I'm closing with. There'll never be another one like him, who had great thoughts while other sights were dim. His modesty, his purity were obvious for all to see. His uber genius was luminous and free. Has physics gotten smaller, or have men? Here, Einstein seems much bigger now than then. There'll never ever be another one like him. There'll never ever be another one like him. And here's a card. Here's a card some friend sent me from Switzerland. Questions? Is there any physicists in the room?